In Egypt, a shipping catastrophe sends shockwaves around the globe.
Her size and her scale fundamentally changed what this event was going to be. This event was going to have worldwide implications.
A devastating bridge collapse in Australia narrowly avoids tragedy.
It was an absolute miracle that people didn't lose their lives, so this is a huge story.
In Pennsylvania, disaster strikes as a driver and his vehicle are swallowed whole.
Usually you'll see a tire or something that goes into a small hole. This actually encompassed the whole vehicle.
And in Louisiana, failure on a crucial crossing forces an urgent multi-million-dollar fix.
$30 million sounds like a lot of money, but compared to human life, you really just can't put a price tag on that.
With big builds, even the smallest mistake can be a huge disaster. From miscalculations to misunderstandings, some with deadly consequences. These catastrophes are every engineer's worst nightmare. Engineers are constantly pushing the limits in both design and scale. But if things go wrong, a catastrophe like the structure itself can be monumental. Like this disaster in Egypt, a crisis on a global scale.
A blockage that was holding up billions of dollars of trade every day.
A super-sized ship runs aground and a race against time to find a solution.
The front of the ship is now trapped, buried in the sand.
They needed to get this ship moved, and fast.
And the world economy is brought to its knees.
She's so large, so big, that when she careened out of control, she effectively blocked 12% of the world's trade in one motion.
Egypt, an ancient land full of epic feats of engineering.
When you say Egypt, you might think of the ancient pyramids, the Sphinx, but it's also home to one of the most vital trade routes on Earth, the Suez Canal.
Linking the Red Sea with the Mediterranean, this maritime shortcut dividing the continents of Africa and Asia is a true engineering marvel. Completed in 1869, it took more than 10 years to build. Associate Professor of History, Dr. Salvatore Macogliano, explains.
The Suez Canal was a massive undertaking. You had to dig 120 miles, 190 kilometers worth of sand and dirt, and it actually conjured up images of the pharaoh building the pyramids. They're building a new pyramid, but this pyramid links together two oceans.
In its more than 150-year history, the canal has become one of the world's most vital shipping lanes.
Previous to the Suez Canal, you had to circle around Africa an additional 15,000 miles in some cases. And it was seen as the bridging of two worlds, something that had never been accomplished before. What the Suez Canal provided was a shortcut.
Today, around 12% of world trade navigates the narrow channel.
In 2020, nearly 19,000 ships transited the Suez, carrying more than 1 billion tons of cargo.
As trade grew, so did the ships, on a mammoth scale. Like this, the Ever Given.
The Ever Given is a giant among ships and can carry 20,000 containers. It's known as Suez Max, the largest type of ship allowed through the canal.
Almost as big as the Empire State Building, these ships are pushing engineering to the very limit.
Ever Given is a quarter of a mile long, 200,000 tons. If you're standing on the lower deck and you look up at the container stack, you're seeing 24 8-foot containers stacked one on top of the other.
With such vast ships, navigating this narrow, shallow stretch of water is no cakewalk. Stephen Turnock is a professor of maritime fluid dynamics.
The Suez Canal, it's very narrow. There's not much water between the bottom of the ship and the bottom of the canal. Sort of the flow underneath the ship is forced through faster than it would normally do, and that kind of sucks the ship down towards the canal bed.
Known as the squat effect, the faster the ship moves through the water, the greater the effect is on the vessel, and the deeper it's forced to sail in the already shallow canal.
Suddenly it matters a lot that you keep within quite narrow bounds, you don't deviate to the left or right by very much, and that makes it particularly challenging for mariners to navigate through and to maintain the course that you want to go through safely.
With only about 9 meters of clearance between the bottom of the ship and the canal bed, any deviation can be catastrophic. During the early morning of Tuesday, March the 23rd, 2021, the 400-meter Ever Given, en route to the Netherlands, was in a convoy of ships traveling north.
It was the 5th vessel in a 25-ship convoy heading up the Suez Canal from the Red Sea into the Mediterranean.
Loaded with 18,300 containers, as the ship approached the entrance to the canal, it encountered heavy winds and a sandstorm blowing from the west. Right from the outset, the ship was struggling to stay on course.
The vessel was never in the center of the canal. It actually maneuvered from bank to bank.
Moving side to side, getting really close on one side, close on the other side, having difficulty controlling its course.
It wasn't just weaving. The Ever Given was also accelerating.
It started to speed up, progressively getting faster and faster, sort of 7, 8, 9, 10 plus knots.
At 7:40 a.m., the 200,000-ton ship crashed head-on into the side of the canal, ploughing around 5 meters into the sandy bank. The Ever Given was stopped in its tracks.
And what the vessel essentially did was ram its bow into Asia. The stern kept swinging northward. It ran aground in Africa. She was traversing the canal at such a high rate of speed that when she careened out of control, she effectively blocked 12% of the world's trade in one motion.
The figures are staggering. It's estimated that the Ever Given was holding up 3.3 million tons of cargo an hour, or $6.7 million a minute.
The ship was completely wedged across one of the busiest trade routes on the planet.
Her size and her scale fundamentally changed what this event was going to be. This event was going to have worldwide implications.
And the world was definitely watching. With the Suez Canal completely blocked and ships and trade at a standstill, the entire planet was searching for answers.
On average, more than 50 ships a day navigate the Suez without incident, and crucially, without making headlines. So the big question was, why did this one get stuck?
Examining the ship's global tracking device revealed that something was wrong from the moment the ship entered the canal. Associate Professor of History Dr. Salvatore Mercogliano explains.
If you follow the track line of the vessel was never in the center of the canal. It seemed to have lost control. It actually maneuvered from bank to bank.
As the investigation began, early reports suggested high winds were to blame. Professor of Fluid Dynamics Stephen Turnock explains that even for a ship weighing over 200,000 tons, this can be a major problem.
With big container ships, they're sticking a long way up into the air. If the wind is strong, then you get quite large forces. A wind was coming from its stern. Naturally, that wants to turn the ship. Actually makes it more difficult to control.
Not only were huge forces acting on the Ever Given from above, they were also at play from below.
The vessel is so large that it doesn't have a lot of water underneath it, and it doesn't have a lot of water next to it along the banks. And that creates forces that act on the vessel.
As well as the squat effect pulling the ship deeper, it was now being dragged towards the sides too by another phenomenon known as the bank effect. As the ship moves closer to the bank, water squeezing between the two surfaces speeds up, pulling the stern towards the canal side, effectively turning the ship.
What we saw happen was Ever Given got extremely close to the west bank, and she had to turn right. And unfortunately, she turned so hard right that it put her into the east bank.
The bank effect was too much of a challenge. You get away from that side, but you then get in trouble on the other side.
While there's little doubt this played a part in the wreck, another question remained. With the initial ships in the convoy making it through, why did this one speed up in the canal?
The Ever Given was reported to be doing 13.5 knots, almost 25 kilometers per hour. That's more than 50% over the speed limit for this size of ship.
The pilots may have actually gone faster to try to get better control of the vessel. The faster you go, the more maneuverable your vessel is. Drive a car down a highway, it takes only a small turn of the wheel to change lanes when you're going fast. The problem was when something goes wrong at that speed, there's very little margin for error.
With the rescue operation demanding help from across the globe, Plan A was to try and pull the ship free. Easier said than done, as geotechnical engineer Professor David White demonstrates. Wet sand is hard to escape.
So in civil and maritime engineering, we use physical models of systems a lot. They're quick and easy to make, and we can just get a feel for the problem. Put it in a tank, got some sand representing the sandbank, and when it comes and hits the bank, it pushes into the bank, and the bow is buried. Dragging the ship backwards, which is maybe the first thought you might have, is very difficult because you've got the friction from that enormous weight resting on the front. If you do a quick calculation, maybe you're going to need 60 or 100 tugs to pull the ship back.
The Egyptians scrambled very quickly. They dispatched tugboats to the area and attempted to pull her off. The problem was, Ever Given being solidly aground on the bow and stern posed too much of a challenge, and it wound up being that the Egyptians could not move the vessel at all.
With billions of dollars of cargo and more than 300 ships backed up on both sides, it was time to go to Plan B.
Twisting it around is easier. If you try to pull the stern of the ship to the side, then actually the force you need is less, maybe just a handful of tugs. And this was the strategy that they adopted.
With larger anchor tugs and a specialized suction dredger, salvage teams were finally making progress.
This specialist suction dredger could shift around 2,000 cubic meters of material every hour. That's almost enough sand and mud to fill an Olympic swimming pool.
So once it was stuck on the bank up here, the dredging here needed to remove the sand over at this side, in front of where the bow is going to push the sand out to allow it to then rotate.
Not only was this one of the most expensive delays in history, it was now also a race against time and the tide.
To free the Ever Given, they used all the resources at hand, even the moon. One thing that all mariners are aware of are tides. And in this case, a fortunate spring tide was happening at the end of the month.
Their best hope was on the Sunday, when water levels would be about half a metre higher than normal for just a few hours. That gave engineers a very real deadline to hit.
The combination of dredging and tugging with some help from the moon finally paid off. On Monday, March the 29th at 3:05 p.m, after 6 long days, the Ever Given was finally free. And while it may be some time before we know the full story behind this crisis, it firmly highlighted the world's reliance on these colossal containers.
We've experienced before hurricanes and disasters that temporarily shut down trade, but never before had we seen an accident shut down 12% of the world trade and all of a sudden impact the entire globe.
After dominating the world headlines for 6 days, finally, this cargo megaship, the length of 4 football fields, was dislodged from the banks and on its way again. Gone, but definitely not forgotten.
In big construction, careful planning and preparation are key to every project. Even a slight mistake and the results can be catastrophic. Like this disaster in Australia that brought down a vital crossing in the capital.
The amount of concrete, the amount of steel that was on the ground over such a large area, I was shocked.
A fundamental oversight that went unchecked.
This disaster could have been avoided.
and a catastrophe that barely escaped tragedy, rocking the nation.
There was shock and amazement, and then obviously it was everyone get to work.
Canberra, Australia's capital, is home to the nation's federal government, as well as national museums and monuments. Local journalist Emma MacDonald was born and bred in this central city.
In 1901, the search was on to find a place for the national capital. Now, there was a big fight between the two biggest cities in Australia at the time, and that was Sydney and Melbourne. They both wanted to be the national capital. So Canberra was in many ways considered a bit of a compromise. It was sort of halfway between the two.
Derived from an Aboriginal word meaning meeting place, every last detail of Canberra's sprawling metropolis was analysed by city planners, and it worked.
Canberra is one of Australia's fastest growing cities, with its suburbs driving much of the population boom.
But as the city grew, the roads were struggling to accommodate all the commuters, especially in the northern suburbs like Gungahlin.
One of the problems with Canberra being such a car-centric city is that the road infrastructure really needs to keep pace with the population booms that these areas have. And Gungahlin was a classic example where we had a lot of development, a lot of new housing, a lot of population wanting to move in straight away, and the roads just weren't equipped.
In 2009, to ease congestion, work began on this interchange. The 9-kilometre Gungahlin Drive extension running into the heart of the city.
Commuters frequently faced lengthy delays any time of day. The work to double the road from 2 to 4 lanes couldn't come fast enough.
In total, 9 new bridges would be constructed as part of the project, including this one, which would be built alongside the existing crossing. Michael Inman is a local reporter.
There was already an existing bridge and an existing drive. They decided to duplicate that so they could have a few different lanes going in each direction so people could actually get to work.
One of the proposed bridges crossed over Canberra's busiest and most important freeway, the Barton Highway. Civil engineer Mike Evans explains.
The road over the top is the Gungahlin Drive, which is the main traffic corridor going in the north-south direction on the west side of Canberra. The road beside me is the main highway through to Melbourne.
Closing this busy highway was not an option. So, like a lot of bridges across major roads, this crossing would be built in place, known as cast in situ.
Cast in situ would allow the busy Barton Highway to remain open. Wooden moulds, known as formwork, would be built in the shape of the bridge, on top of the temporary steel bracing or supports. The plan was to cast the entire deck in one pour, and once hardened, lower it into place alongside the existing bridge, creating a 4-lane crossing.
The extension was vital, not only to Canberra's transport network, but for the growth of the city as a whole.
Saturday, August the 14th, 2010, the concrete pour was underway. At around 1:50 p.m, workers were over 3/4 of the way through.
They heard a bit of a cracking sound, and about 2 or 3 seconds later, the bridge just gave out from underneath them.
A huge section of the bridge collapsed suddenly and without warning. Workers scrambled for their lives as hundreds of tons of wet concrete came crashing down onto the road below.
Some guys had time to run clear. Several guys went down with the bridge.
Incredibly, one worker managed to grab hold of a cement truck hose and clung onto it in mid-air for around 15 minutes until he was rescued.
With Canberra's main highway now blocked, details of the disaster quickly spread through every newsroom in the capital. Journalist Emma MacDonald was at work when word came through.
I remember all of us just being quite shaken because the people that were working on that project were people who lived in Canberra, and everyone knows everyone in this city. There was shock and amazement, and then obviously it was everyone get to work. This is a huge story.
As reporters and rescue workers rushed to the scene, the scale of the disaster became clear.
When I first saw it, I thought to myself, you know, what a mess. I'd never seen anything of that size and scale to collapse like that. The amount of concrete, the amount of steel that was on the ground over such a large area, it blew my mind, to be totally honest. I just thought that these things don't happen in Australia.
While 15 workers were injured and 9 hospitalised, incredibly, despite the devastation, no one was killed.
Those workers were just so lucky. It was an absolute miracle, given the catastrophic nature of that collapse, that people didn't lose their lives.
The disaster sent shockwaves around the country, and people wanted answers.
Well, everyone was interested. Everyone in Canberra was speaking about it. So it was obviously a big story around town and nationally at the time as well. The question then started to be, how did it happen? Why did it happen? And what was the fallout?
In a city famed for its planning and heavy reliance on its road network, how had such a seemingly routine build gone so disastrously wrong?
And we've got to figure out what happened, make sure it doesn't happen again. But at the same time, you know, there's a highway that's been blocked. There's a major road that's been blocked. So they've also got to get that moving so the rest of the town can get moving again.
An engineer's report commissioned by the Australian government quickly identified the source of the problem. The steel beams supporting the wooden mould or formwork were missing a key structural element. Civil engineer Mike Evans was asked by the government to analyse the findings.
The beams on the temporary bridge had no bracing and no stiffness, and that lack of bracing and the instability of the beam reduced the carrying capacity of the beam. This is a photograph of the temporary bridge, and you can see from this that these are the longitudinal steel beams with the timber resting on them. There is no cross bracing of any kind.
The investigation found that the steel girders supporting the formwork weren't braced to prevent lateral movement. But when you're pouring around 800 tonnes of wet concrete, one thing you're going to get is movement.
Engineers also discovered that the steel supports had been placed at a slight angle.
The beams had been placed at 3% to the vertical so that the rain could run off the surface of the road. Now, gravity acts vertically, so in effect the beams were carrying a sideways load at the top of about 3% of the vertical load, which, whilst a small proportion, was a very sizable load.
It was more than enough to make the temporary structure unstable.
A combination of the lateral instability, because it wasn't braced, plus the fact it was carrying a sideways load, caused the beam to move over sideways and to bend sideways and then eventually to flip over.
Essentially, they didn't have the weight-bearing capacity underneath the bridge, and the whole thing just crumpled out from underneath them.
Further investigation also found that the welding of the top beam was insufficient.
What was critical in this case, they only did a partial weld rather than going through the full depth of the metal. But because of the sideways bending as well, there was a tension on the edge of the top of the beam, and that caused that to tear open. If you look at this close-up, you can see the rusted area where there was no weld. It's only that little edge there where there was any weld. Not a very good detail.
The report cited multiple structural and planning failures that ultimately caused the disaster.
In fact, engineers often talk about the Swiss cheese effect, where all the holes in the cheese have to line up to cause the accident. And I think this may have been one of those cases where so many things went wrong all at the same time. You had the end effect of the bridge collapsing during construction.
Following the catastrophe, engineers were quickly deployed across the city to check all other bridges under construction.
Fortunately, this flaw in the formwork was only found in this one bridge. The others being built around Canberra at the time were given the all clear.
In the aftermath, new regulations were put in place for formwork and the bridge demolished.
It took a month to clear all the debris away. I think it took another 4 months until they could even start trying to construct it properly again and get the project actually finished.
A new crossing was rebuilt, and the Gungahlin Drive 4-lane extension finally opened on October the 7th, 2011.
And it looks lovely now. You go up and around and off you go. Very, very few traffic jams, if ever.
With lessons learned and a new code of practice in place for formwork, hopefully disasters like this will be a thing of the past.
Australia has been nicknamed the lucky country. In this case, it's a miracle no one was killed.
From the tallest towers to our vast sprawling cities, engineers build to last. But there's no escaping the ravages of time. Like this disaster in Pennsylvania that struck without warning.
All of a sudden, the road opened up and swallowed his SUV.
A massive sinkhole in the middle of a suburban street.
Usually you'll see a tire or something that goes into a small hole. This actually encompassed the whole vehicle.
Leaving residents wondering, how did this neighborhood nightmare happen? Easton, a small city in Pennsylvania, owes its existence to the ground on which it sits. Brittany Sweeney is a local journalist.
Easton is a little town. It's really rich in natural resources like limestone, slate, and iron ore. The other great thing about Easton is it's located in a region that has a lot of highways, so it's easy to get products in and out of this area.
The city might be looking to the future, but it can't escape the past beneath its feet, which is far from solid. Geotechnical engineer Ward McMasters explains.
Easton is part of one of the limestone belts that basically run across Pennsylvania and then dip down into Maryland, known for sinkholes characterized by the limestone bedrock below. Limestone, just because of its geologic characteristics, is going to have fractures and cross fractures, and also what you're going to have is voids within the bedrock system.
Because the more people you have, the more water gets used, which dissolves more limestone.
When we exacerbate it by having larger developments, concentration of people piping below the ground surface, we cause increased levels of sinkholes.
Water dissolves the limestone, forming fractures and voids which grow into caves. As the roof gets thinner and collapses, the soil above is washed away, creating a sinkhole.
The ground can be riddled with holes, but from the street level, you'd have no idea. If you then build a city above them in time, it can be a recipe for trouble.
Monday, December the 30th, 2019, on a suburban street in Easton.
This is a quiet neighborhood where not a lot happens.
As residents were going about their daily business, all that was about to change.
From the footage, this looks like a regular rainy day on a regular street. Then, the SUV kind of bumps and drops into a hole. It's surreal.
Journalist Brittany Sweeney knew this big hole was big news.
Not a lot of people traveling through. It's not like it's a busy road, so the fact that a sinkhole would open up and just driving down the road and then all of a sudden your car gets swallowed by a sinkhole, that is an insane thought for a neighborhood like this.
It was more than that. A young girl was watching from her bedroom window.
I couldn't believe it that it was my dad's car. So I rushed downstairs. My mom was in a panic.
Her father was trapped. Easton Fire Chief Henry Hennings was on duty at the time.
When I pulled up to the intersection, I saw the front end of the SUV sticking up in the air, and the original sinkhole opened up right about this area here, and it was pretty large. It was probably 40 foot in diameter and at least as deep.
The hole was filling with water, with the driver fearing for his life.
And I see a lot of water is going through. That's time I'm scared, you know? So I'm going to die right now.
Luckily, both the driver and passenger scrambled to safety.
It was a relief that it was a recovery and not a rescue. We didn't have anyone hurt, which is always fortunate.
But the danger wasn't over just yet.
Once the sinkhole opens, there's no way of knowing where it's going to go or any way to stop it.
Pretty much every built structure has foundations. And if the foundations have been washed away under part of the road, there's a risk the same is happening elsewhere, even under the buildings nearby.
When you have a sinkhole in a residential neighborhood, any of the housing in the area is at risk.
Houses on both sides of the street were evacuated, and more was to come.
That first sinkhole was not the last. A few days later, as they're working to fix the street, an excavator fell right into the street, into another sinkhole. It was scary for the neighbors. They said that it started to get to a point where they never knew when another sinkhole was going to open up under this street.
While this part of Pennsylvania may be famed for sinkholes, there were no known caves directly under the neighborhood. Engineers ruled out Mother Nature. Something else must be at fault.
Easton had a water main break, but the water main break wasn't in the actual location where this sinkhole occurred.
With no direct flooding causing the sinkhole, how had it opened up so dramatically?
When a water main breaks, the escaping water can blast a hole under the road surface. But sometimes, like here, the water tracks underground, causing erosion further down the road.
That fracture becomes very active, and 50 feet down the road, 100 feet down the road, all of a sudden we get a sinkhole that appears to have cropped out of nowhere. But a lot of times they are interconnected just at depth.
The broken water main explained the sinkhole. But the next question was why it had failed in the first place.
In the US, there's a water main break roughly every 2 minutes. The basic reason is simple: age.
Like many water pipes in America, this could have been a century old, and back then most were made from cast iron.
Cast iron piping can be susceptible to increased brittleness when we have cold water temperatures moving through it. It doesn't have to be freezing. Anything below 40 degrees will increase the brittleness of that piping.
The problem here isn't the water pressure bursting the pipes, but the cold temperatures of winter making the cast iron brittle. Multiply that by nearly 100 cold winters, and it's no surprise that they fail.
Once the water washes away the road's foundations, it's only a question of time before a sinkhole appears.
This is really a scary thought for the people who live in this neighborhood, and any neighborhood for that matter. It's not like it's a street that's heavily traveled, it's not a highway. This is just a neighborhood road that is in a suburban area, and for a sinkhole to open up when someone's just driving down the street is just scary to think about.
Across the US, there are more than 3 million kilometers of water pipes, much of them still cast iron. Yet since the 1960s, one new material of choice has been ductile iron. Although installing it is an expensive and disruptive process.
What we want to do is, when the budgets allow, let's go in and get rid of the cast iron piping and replace that with newer, more updated materials that would be stronger and more resistant to the weather.
The graphite in cast iron is flaky, and those sharp edges make it prone to cracking. In ductile iron, however, the graphite is rounded, and that acts as a crack preventer. So pipes made from ductile iron are stronger, more malleable, and more durable as well.
To make sure that we can maintain the stability of the roadways and the buildings to protect the health and safety of the people of those areas.
In a city built on soluble limestone, this sinkhole was a reminder of the risks of aging water systems.
The US has a massive problem with aging infrastructure. There's no silver bullet, but shocking events like this are a good reminder to everyone that one day, nearly all of it needs repairing or replacing.
With all bridges, gravity can be an engineer's biggest enemy. But when other forces come into play, the threat can be much greater. Like this near miss in Louisiana on a crucial river crossing.
This is an evacuation route. It's a route that needs to be kept open.
This fail had been brewing for decades and prompted a major rebuild.
$30 million sounds like a lot of money, but compared to human life. You really just can't put a price tag on that.
An oversight with the potential to bring this mighty bridge crashing down. New Orleans, Louisiana. More than 1 million people call the metropolitan area home. In this low-lying city, life is ruled by the water that surrounds it. Autumn Cafiero Giusti is an engineering journalist.
We're in Southeast Louisiana. This is an area surrounded by large bodies of water, swampland, the Gulf of Mexico. We've got the Mississippi River.
With half the city below sea level, flooding is a very real risk, whether from the Mississippi or storm surges from the Gulf.
We're right in the path of hurricanes being right by the mouth of the Mississippi River. If there's a storm that's large enough that could overtop those levees, that's when we have the bowl effect where the city starts to fill up with water.
New Orleans floods most years, but when Hurricane Katrina hit, parts of the city were inundated for more than a month. More than 1,500 people died in one of the worst disasters in US history. But the toll could have been higher. More than 80% of residents had fled New Orleans in the city's first ever mandatory evacuation.
Evacuating can be a very dramatic response, but when you're in the direct path of a hurricane, moving can be the safest option.
And if the city starts to fill, for most, the only way out is by road.
You have something like a Katrina where you've got an entire metro area trying to leave, all of your roads are going to be congested. So having reliable roadways that you can use to get out of the city, every possible artery is necessary.
With so much water to cross, bridges play a crucial role in the evacuation plan.
These bridges across the Mississippi, there are only a handful of them, so they're really vital because that is our way out of danger. That is how we escape the city.
This key Mississippi crossing, about 40 kilometers west of New Orleans, is the Hale Boggs Memorial Bridge.
Coming out of the city, you go from suburbs to just swamp all of a sudden. You turn onto 310, and then all of a sudden there's this big, beautiful bridge kind of out of nowhere. So impressive to look at.
Completed in 1983, with a main span of around 370 meters, this was the third major bridge of its type in the US. Norma Jean Mattei is a professor of engineering.
It was a very innovative bridge. Back in the 70s when it was designed, it was the first cable-stay bridge to be used to cross the Mississippi River. There were cable-stay bridges in place in Europe and in other parts of the United States, but a cable-stay bridge crossing the Mississippi had never been done.
One main challenge was to build a bridge that wouldn't obstruct the busy shipping channel below.
You can see that the Mississippi River is a pretty wide river down here in Louisiana. So you want to not have the substructure too close to the navigation channel because you're going to have major ocean-going vessels pass it, and should one lose control, you do not want that vessel to collide with your bridge pier.
With Louisiana's famously swampy ground, a cable-stay bridge was the best solution to keep the shipping lane as wide as possible. The main towers stand on bedrock, taking the strain of the 72 steel cables that support the road deck below.
Those cables are protected by a polyethylene or plastic sheathing, and you don't want water to get in between the sheathing and the steel cable because that would cause rust.
Back in the 80s during construction, the plastic covering the original cables started to crack before they were even erected. Engineers were able to patch up 21 of them, but it was too late to replace them completely.
The cables were already in tension, so all they could do was try to repair them for now. The plastic was heated to seal the cracks, but the real damage had already been done.
In 1983, with the cracks repaired, the Hale Boggs Bridge opened to traffic. 2 decades later, when Hurricane Katrina struck, the bridge stood firm and played its part as a vital evacuation route.
When I evacuated for Katrina, I think we took the Hale Boggs Bridge out of town because it was less jammed with traffic. So it really is important to getting people out.
Just 2 years after Katrina, another catastrophe further up the Mississippi raised red flags.
In 2007, the Minneapolis I-35 bridge, also over the Mississippi River, collapsed. This was kind of a turning point for infrastructure in the United States.
Hale Boggs was newer and a completely different design, but no chances could be taken.
This is when people really started paying attention to the state of our infrastructure and the fact that things needed to be repaired.
In 2008, the original cables went under the microscope with concerning results. Although the bridge could survive the failure of individual cables, more than half were found to be corroding, reducing their ability to carry the weight of the road below.
The amount of tensile force that a cable can carry is a function of its ultimate tensile strength and its cross-sectional area. If you have corrosion, you have just removed some of that cross-sectional area, so you no longer have the same amount of area to hold that tensile force.
Although none of the cables failed, the corrosion was far worse than expected. If it hadn't been spotted, the results could have been catastrophic. Action needed to be taken, and fast.
As engineers investigated further, they discovered the problem was being made much worse by Louisiana's wet and windy weather.
The cables were very well monitored, and what was noticed that in rainstorms, the cables would vibrate. And that was not something that was foreseen.
As wind from the storms caused the cables to vibrate, it was creating stress and fatigue on the steel inside, as well as cracking the anti-corrosion sheathing meant to protect the steel. With more than 50,000 vehicles crossing the bridge daily on one of the city's main evacuation routes, it was crucial this vital bridge was fixed for good.
When they were repairing the bridge, they really had to take into account evacuation traffic and loads and figure out if the bridge could support that much weight, because when you have an evacuation, you're going to have a lot of cars on the bridge, and that puts a lot of stress and strain on the bridge.
In 2009, the decision was made to replace all 72 cables.
There was a lot of thought and design that went into how do we economically and safely replace the cables and not impact the ability to move traffic along the bridge. Now that's a challenge because this is an evacuation route. It's a route that needs to be kept open.
To keep the bridge operational, the cables were replaced individually, one side at a time. And to prevent wind-induced damage, the new protective sheathing has a ribbed exterior design.
This was an incredible fix. Every cable was successfully replaced one by one, allowing the bridge to remain open to traffic throughout.
Now, the bridge was better than new, but the fix hadn't come cheap.
$30 million sounds like a lot of money, but compared to human life that could have been lost if it hadn't been repaired, I mean, you really just can't put a price tag on that.
Work was completed in 2012, and the new cables are set to last for 3/4 of a century.
Knowing that it's been repaired, that it's got, a new lease on life and 75 years of lifespan is really reassuring, and I think it's going to be reassuring to the people who use this bridge all the time.